Hello, everybody. Welcome to lecture 7 about memory hierarchy. In this lecture, we will be talking about memory hierarchy. The main context of this will probably be like an introduction to memory hierarchy, um, the classifications of memory, the capacity and the organization as well as on-chip memory and the off-chip memory, the difference between them. The DRAM technologies which fall under the off-chip memory, and we'll get to that and then some emerging trends and issues about memories. Um, but no further delay, let's pop in. Just an introduction to memory hierarchy. The need of memory hierarchy is to bridge up the speed gap between a CPU and the main memory. There are different types. There's an on-chip, which is a cache, can be L1, it has a level 1, level 2, or level 3 for quick access. And then there's also the off-chip. And for the off chip, it's a DRAM, and it's usually for larger capacity. There's classifications also for memories. There's an SRAM, and there's also a DRAM. An SRAM falls underneath a cache memory, and a DRAM underneath it falls a main memory. The difference between them is that an SRAM is fast and it's used for caches, and then for DRAM, it's larger, but it is a little bit slower. And the last type is probably going to be the non-volatile over here on the right. There's a design showing how the increase in cost per bit increases according to the levels from level 0 up to level 4. The lowest level has the highest cost, and as for capacity, the highest level has the highest cost. Recent trends about these would probably be like the hybrid memories or the Rohammer effect or the in-memory computing, which will get into some of them later in today's lecture. Nevertheless, now about the memory classification. There are volatile memories. There is a DRAM, there's an SRAM, and there's also non-volatile memories, which are like a flash or a ROM or EPROM, a random only memory. The DRAMs and the SRAMs, the DRAMs are volatile. They store data using capacitors and transistors. As for the SRAMs, they use flip-flops for data storage. Flashes are like USBs or SSD drivers. Random only memories used for firmware storage. As for the access mechanism, that falls into random access memory, which is a memory or RAM memory, and also a serial access memory, a SAM, as well as a CAM, which is a content addressable memory. And the difference between every single one of them is that a random access memory can be accessed in any order. As for the serial access memory, the data is accessed in a predetermined sequence. And as for the CAM, which is the content addressable memory, the data is accessed based on content rather than address. Nevertheless, over here we're talking about some memory capacity and organization. The memory chip capacity measured in K bits, M bits, and etc. They also indicate the total amount of data the chip can store. As for the memory organization, chips are organized into multiple locations. Each location can store a specific number of bits, depending on the amount of bits. Sometimes it goes like 1 bit, 4 bits, 2 bits, depends on it. As for the speed, it accesses time typically measured in nanoseconds for how fast it is, and the trade-off between memory size, speeds, and costs. Over here on the right, there's a diagram showing the cost, speed, and size and how they can increase. They increase, so like a regular memory has the highest cost and high speed. Now level 1 cache has a higher speed than a level 2, and a RAM has a lower speed than a level 2, and then a secondary memory which falls over here. It has the largest size, but that means that it's the slowest and it costs the least. Next over here, we're talking about an on-chip memory. So on-chip memories, over here we have a diagram showing how the levels of memory in an operating system, how it goes from a register file to a cache file, and how that's all like on one microprocessor. And then from that, it goes to a different level into the main memory and then to the secondary, and then it can go into like from a secondary memory is like a hard disk. From there, you can also store it onto a cloud, which also can fall under secondary memory. Registers, they're very quick in access time. They have limited number of registers available. They require dedicated assembly instructions for access. So as for the cache levels, there's level 1, level 2, level 3. As we spoke earlier, the level 1 is smaller yet faster. And then as you go down, they change. The higher the level is, the slower it is, but the larger it is. As for the difference between an instruction and data cache, the instruction cache is pretty much it stores instruction to be executed. The data cache stores frequently accessed data. Next, we're going to talk about an off-chip memory. Over here, we're talking about DRAMs. Specific over here, there's a diagram of how a DRAM looks. It consists of a transistor and a capacitor. That's the basic DRAM schematic. A DRAM technology, each bit stored using a transistor and a capacitor. They're larger in integrating compared to an SRAM, and they're also cheaper to produce. They require periodic refreshing, but they're a little bit they're slower than the SRAMs. There are different types of DRAMs though. There's a DDR, there's a DDR2, and there's also a DDR3. DDR means double data rate, and the DDR1 pretty much transfers data on both rising and falling edges. DDR2 improved version of DDR, and then the DDR3 has a further improvement than the DDR2. There's also memory modules such as the single inline memory module and the dual inline memory module. And the dual inline memory module is usually used in modern computers. Over here we're going to talk a little bit about DRAM technologies. So an SDRAM, which is a synchronous DRAM, it's synchronized with a system clock and it transfers data in sync with the clock signal. So over here on the right, we have a diagram showing an SDR compared to a DDR1 and DDR2. As you can see, the SDR has only 1 bit, and then DDR1 has 2 bit. And then as for the DDR2, it has a 4 bit. As for the DDR3, in this case, it will have an 8 bit though. Nevertheless, over here, we're just going to talk a little bit about emerging trends and issues. A hybrid main memory. It combines different memory technologies. An example of that would be like combining DRAM with a non-volatile memory like a PCM, for example. And there's also the Rowhammer effect, which has disturbances in the DRAM, and repeatedly accessing a row can cause bit flips in adjacent rows, potential security vulnerability. Solutions for this would be improved DRAM chips with better error correction and more frequent refreshing of memory cells. And memory computing, however, has processing data directly within memory. It reduces data movement. An example of that would be like near memory computing, processing memory. Just a conclusion, just a recap of what we went through today. We covered memory hierarchies, memory classifications, and on-chip versus the off-chip memories and how they're different, and the roles of the caches in the DRAM and the memory hierarchy. And then we just went a little bit over some emerging trends under like a hybrid memories, the Rowhammer effect, or in the in-memory computing. That was it for today. Thank you so much and have a good day.